All right, Calc AB, here's 4.6, day 3. Number 1, if the volume of a cube is increasing at 36 inches cubed per minute and each edge of the cube is increasing at 4 inches per minute, what is the length of each edge of the cube? So we have to remember that a cube has all the sides that are the same, and the volume of that cube is going to be equal to the sides squared. So if we say that every single one of these sides is equal to x, then my volume is equal to x cubed, and take the derivative with respect to time. So that's our derivative equation, and now we can make substitutions. The volume is increasing at 36 inches cubed per minute. We don't know the length of the edge of the cube, so we'll leave this as 3x squared. And we do know that each edge is increasing at 4 inches per minute, so we'll multiply by 4. And so now we'll solve. So 36 equals 12x squared. X squared is equal to 3. X is equal to, generally it's plus or minus root 3, but because we're dealing with a geometry context, we're going to just use the positive case and throw a unit on there. So our answer is root 3 inches. Number 2, if the volume of a cube is increasing at 36 inches cubed per minute and the surface area of the cube is increasing at 4 inches squared per minute, what is the length of each edge of the cube? So we still have the exact same volume equation that we just had, but we also have to consider what the surface area of that cube would be. And because all the edges are the same, all the faces are going to have the exact same area. So there are 6 faces, and all of the areas are equal to x squared. I'm going to take derivatives of both. Make substitutions where I can. So we know that the surface area is increasing at 4 inches squared per minute. And then I'm going to solve for dx dt. So the dx dt is not going to have like a numeric value just yet, but I see it here, and then I see it over here, and those values have to be exactly the same. So dx dt is the same thing as 1/3 times 1 over x, or you could write it as like 1 over 3x. So then that gets substituted in over here into my volume derivative. We can also replace dv dt with the 36. And now we solve this equation. So my 3's cancel. X squared over x is going to become x. So x is equal to 36 inches. So there are 2 questions that sound sort of similar, like both of them had the volume changing by 36 inches cubed per minute. But one of the questions was giving you how the edge of the cube was increasing, and in number 2, we were giving you the surface area increasing. So the questions are approached a little bit differently. And number 2 just requires a substitution. All right, number 3. A particle is moving around a circle with a radius of 17. At the point 815, the particle has horizontal velocity dx dt equals 4. What is its vertical velocity dy dt at that point? So we have a point 815, and we know for sure that the circle has a radius of 17, and at the moment in time we're dealing with the point 815. But remember that it doesn't have to be 8 and it doesn't have to be 15, but we always do know that the radius should be 17. Okay, so I still see that this is a right triangle. So x squared plus y squared is equal to 17 squared. take derivatives of all of these parts. So 2x times dx dt plus 2y times dy dt is equal to 0. And now we can make substitutions with what we know. So we know my x is equal to 8 and my y is equal to 15 because it's at that moment in time. So 2 times 8 times 4 plus 2 times 15 times dy dt is equal to 0. All right, so we'll solve this for dy dt. 2 times 8 times 4 ends up being 64. So I'm going to move that to the other side. 30 times dy dt is equal to negative 64. dy dt is equal to negative 64 over 30. And there were no units given to us in the problem, so we don't have to worry about units here with our rate. So what's interesting here is that the rate for x changing is positive and the rate for y is negative. And that information tells us that this particle is actually traveling the circle clockwise. And it's because the x distance has to be getting bigger and the y distance has to be getting smaller. So they didn't tell us that. They just said that the particle is moving around a circle, but knowing those two pieces of information tells us that the particle is moving clockwise. All right, number 4. A man 6 feet tall walks at the rate of 7 feet per second toward a streetlight that is 20 feet above the ground. At what rate is the length of his shadow changing when he is 10 feet from the base of the light? The first thing that we're going to want to do is draw a picture. And so here's our person. And here is the street lamp. And if you remember these problems from geometry, they are always about similar triangles. And we're going to assume that we have a perpendicular situation. And throwing in some numbers here, the man is 6 foot tall. The street lamp is 20 feet. And so then we can divide up the base down here into two different distances. So I think x represents the man's shadow, but then there's also this distance that the man is from the street lamp. And so these two triangles are similar. So here's one of the triangles, and then there's the overall large triangle. And so the equation that we can write for this is vertical over vertical is equal to the horizontal divided by the other horizontal. The biggest thing to remember is that in that big triangle, it's the entire length of this side. And so you can't just say d, it has to be d plus x for the entire length of that side. All right, so cross multiply. And move your x's to one side. So we have 14x is equal to 6d. And now I'm going to take derivatives. So you could have taken derivatives like at this point, but I think that this is a more complicated derivative to do, right? It's a quotient. So what I'm doing is getting my variables, like variables on one side, and then it's easier to take derivatives. So the derivative of 14x will just be 14 times dx dt equals 6 times dd dt. Okay, so looking back at the problem, a man 6 feet tall walks at the rate of 7 feet per second toward a streetlight that is 20 feet above the ground. At what rate is the length of his shadow changing when he is 10 feet from the base of the light? So I see this 10, and 10 represents d, but when you look back at this equation, there is no d there. And so it actually doesn't matter. So at that moment in time, or at any moment in time, this distance the person is, or this man is, from the street lamp will not matter. The rates are telling us that it doesn't matter. So the only thing that you have to put in is dd dt, which is how that distance is changing. And because the man is walking toward the street light, that d value is actually getting smaller and smaller. He's getting closer to the street light. Therefore, that 7 should actually be a negative 7. So 14 times dx dt should be equal to 6 times negative 7. Therefore, dx dt is equal to -3. Throw some units on there, so -3 feet per second. So that's an interesting idea too, that this shadow rate is negative, and that means that the person's shadow is actually getting smaller because the person is walking closer to the street lamp. And that's because, if you think about it, the right triangle is getting taller. And so that distance here should be getting smaller and smaller. All right, so that's problem 4. Here's problem 5. An airplane is flying on a flight path that will take it directly over a radar tracking station. The plane is flying at a constant altitude of 6 miles above the ground. If the distance between the radar and plane is decreasing at a rate of 400 miles per hour, when the distance is 10 miles, what is the speed of the plane? All right, so we're going to draw a plane. And that plane is flying at a constant elevation or constant altitude of 6. So I am going to make this be a right triangle, and that's going to be 6 miles high. Here's the radar. And so we have 2 different values here. Let's call this h, let's call this x. And so here we are governed by a right triangle again. So we have x squared plus 6 squared equals h squared. Take derivatives. And then we can plug in what we know. So if we know that the plane is decreasing at a rate of 400, the distance between the radar and the plane is decreasing, that represents dh dt. So that should really be a negative 400 because it's decreasing. And we know that when the distance is 10. So like at the moment in time when this distance is 10, this has to be 8. And you can either figure out that it's 8 through Pythagorean theorem, or you can remember the family. The Pythagorean triple is 3, 4, 5, so then you can multiply by 2, so it's 6, 8, 10. So you'll make substitutions here. So 2 times 8 times dx dt is equal to 2 times 10 times negative 400. And when you solve, you get that dx dt is equal to negative 500 miles per hour. All right, the last one that I'm going to do with you here is number 6. A particle moves along the portion of a curve r equals 3 plus 2 cosine theta for 0 to pi over 2. The particle moves in such a way that the distance between the particle and the origin increases at a constant rate of 3 units per second. Find the rate at which the angle theta changes with respect to time at the instant when the position of the particle corresponds to theta equals pi over 3. Indicate units of measure. All right, so this is a long problem. There's a lot of words. It's sort of intimidating here because you've got thetas. But I want you to remember back to pre-calc that this is a polar graph. And so remember that when you have polar graphing, that the distance out here is the radius distance. So like just putting that together, this distance that they're talking about, the distance between the particle and the origin, does correspond to this exact same r. They're not coming out and saying it directly, but that's exactly what they mean. They want you to recognize the polar function. So all you have to do then is take the derivative. So dr dt is equal to, I forgot a 2 and I had to go back. So when you take the derivative, you should have a negative 2 out in front, and then the derivative of cosine is negative sine, and don't forget to multiply by that d theta dt. So now plug in what we know. We know that the distance between the particle and the origin increases at a constant rate of 3 units per second. So that is exactly the same thing as dr dt. So 3 equals negative 2 times the angle is pi over 3. And we still have to find d theta dt. That's the question. Pi over 3 is a 60-degree reference, and the sine of pi over 3 is going to be root 3 over 2. So my 2's will cancel out, So d theta dt equals 3 divided by negative root 3, which is the same thing as negative root 3. You don't have to do that. I'm just showing you the equivalence here. And then put some units on it. So the angle is in terms of radians, and your unit of time is in seconds. All right, so that's it for what I'm going to show you here. I want you to try the remainder of the questions, and we'll Zoom together in a few minutes.